Okay, so off we go. All right, so we just finished the two longest units of the year, stoichiometry and gases. Gases is primarily actually the kinetic molecular theory, but now we're doing the shortest unit of the year, and that is state equilibrium, which is still kinetic molecular theory, but it has to do with the three primary states of matter. So we're not going to worry about plasma or Einstein-Bose condensate. We're just going to focus on solid liquids and gases. Now, quick reminder, the kinetic molecular theory tells us all matter is made of particles in constant motion. All matter? Yeah. So it's really easy to see where these particles are in motion, but are the particles of this desk also in motion? Yeah. They're just not moving very much. Much like you're emulating a solid, you are fixed in position, and you're kind of moving around a little bit. But solid particles are also fixed in position, and they're not moving very much. This unit is all about the battle of kinetic energy and intermolecular forces. Two concepts you've actually learned before. What is kinetic energy? Movement energy, right? So kinetic energy is movement energy. If you remember, 1/2 mv squared. So when particles move more, they have more kinetic energy. A higher temperature is a higher kinetic energy because temperature is kinetic energy. Make sense? Now, you might not remember intermolecular forces. You learned about intermolecular forces in bonding back in November. What are intermolecular forces? They are cohesive forces, yeah. Intermolecular means between molecules. So intermolecular forces are the forces that molecules use to stick together. If you remember water is polar. Water has a partial negative end and a partial positive end. So the partial positive end of one water molecule will be attracted to the partial negative end of another molecule. And the chain will continue till all the water molecules stick together. Make sense? Yeah? Okay, give me a thumbs up if you understand what the intermolecular force is. Okay, wave your hand around if you need to say that again slower. Okay, so intermolecular forces are the forces of attraction that molecules use to stick together. So if you remember, we have a water molecule, and water molecules are H2O. There's our O, there's our H, and with two unshared pairs chilling out down here. So water molecules have a partial negative end and a partial positive end. So if you drew the water molecule, you'd have a partial negative end and a partial positive end, and we show that with a dipole. Cool? So if you have a whole bunch of water molecules, you have another water molecule coming along, the partial positive end will be attracted to the partial negative end of water's partial negative end. And then the partial positive here will be attracted to another water's partial negative. Those are intermolecular attractions. And when we're talking about states, what we're talking about is the battle between intermolecular attractions and kinetic energy. We're talking about state changes, we're talking about one becoming bigger than the other. Okay. Next, the vast majority of this unit, why we call it change the state. We're going to call this physical equilibrium. You might notice on the notes it's called physical equilibrium, is because we're going to look at two things happening at the same time. What does equilibrium sound like?
Equal.
Equal, okay? Just like chemical reactions are equal, but equilibrium is a dynamic equalness. It's where multiple things are happening at the same time. For instance, let's say you're working at, God help you, Best Buy on Black Friday. Yeah, Best Buy at any time. Ugh. You have to leave there and take a shower. So imagine Best Buy. It's Black Friday, like 4 o'clock in the morning, and you saw a bunch of people, and they open the door, and people are like, "I need to buy more crap," and they're all running in like, "More crap!" So they're all running in to buy their crap, and people are flooding into the store. Are people going to constantly flood into the store? Like constantly and no one's going to leave? Till the store just explodes? No, people will eventually leave. And as they buy their crap and they leave, the number in the store will drop. Well, eventually, the number of people going into the store and the number of people going out of the store will be the same. They're not going to be the same people, but they'll be the same number. So if you took a count, you're like, okay, 9 o'clock, all right, there's 400 people in here. 1 o'clock, There's still 400 people in here. Are they the same 400 people? No. But as people go in and people leave, we create an equilibrium state where there's an equal number of people in the store, even though they're different numbers of people. Or different people. Make sense? So that's how chemical reactions and physical reactions happen. You have a state where it's all reactants, and then the reaction happens and they go zoom to products, but eventually the zooming slows down and slows down and slows down, and eventually some of the reactants are becoming products and the products are becoming reactants, and it's happening at the same time. The forward reaction and the reverse reaction are happening at the same time. So we show that with a double arrow. It looks like this. It's like half an arrow, half an arrow. That is the equilibrium symbol, which I cannot draw in Microsoft Word for the life of me. So you'll see it in different ways, but basically an arrow on both sides basically means equilibrium. Cool? All right, cool. So now chemical equilibrium we'll talk about in April. In this unit we're talking about physical equilibrium, states, where you have freezing and melting happening at the same time. Specifically, imagine you got some iced tea, and you're like, look at the ice cubes, like I'm gonna put in 5 ice cubes in my iced tea. And then after a while you look down and you're like, my ice cubes have frozen back together. I thought ice cubes only melt in water. Anyone ever seen that? Where ice cubes melt back together? Yeah. That's because at 0 degrees, the ice is both melting and freezing at the same time. So what's the freezing point of water? 0 degrees Celsius. What's the melting point of ice?
100.
The melting point of ice is 0 degrees Celsius. So if you have a jar of water with ice in it, at 0 degrees, the ice is both melting and freezing at the same time. That's called a state equilibrium or a physical equilibrium. Cool? You're like, give us something to write down. Okay, fine. Okay, so let's just quickly back up one step and talk about distributions. Remember this? This is the distribution of energy on the x-axis and number of molecules on the y-axis. So you got a distribution. Look at the pretty distribution. And when you look at temperature, it is an average of the kinetic energy. Blue being the cooler temperature, average 25. Red being the warmer temperature, average of 35. And who can tell me with showing their hands, raise their hand, tell me, why does water evaporate at room temperature? First come, first serve. Raising the hands. Okay, great.
Because of the outliers on the opposite sides of the spectrum, where it's like some are at the boiling point and others obviously are at line.
Yeah. Here you go. She got them both. So yeah, water boils at room temperature, just not very much. So there's a few particles down here that have enough energy to leave into the gas phase, which is why water, a puddle of water at room temperature, will eventually evaporate. Okay, so average distribution, okay, so talk about that. Solids. When you hear the word solid, what is an adjective that you think about? Hard. Excellent. What else? When you think solid, you think hard. What else do you think? Rigid? Excellent. Okay, so rigid basically not moving. Stable? Okay, what else? Those are all excellent adjectives. So hard, rigid, stable. What about, if I drop this into water, what's it going to do? Sink, because it has a lot of what? Density. Solids are usually dense. Okay. All those adjectives, all those properties come about because solid molecules do what to each other?
Connect.
Excellent. They attract. Yeah, they connect. So I'll take connect. Connect's a good one. You get a red one. And I'm thinking it was probably sunny, but I couldn't hear. I heard something in the back.
I said rigid.
One for the ants. Okay. You're right. You did. Thank you. Okay. So yeah. Make sure we get that one at some point. It's back there somewhere. So all those adjectives that we came up with for solids all have to do with the same thing that solid particles are doing. They are attracted to each other. They are connected in a fixed lattice. Much like you are fixed in position, Until the bell rings, you are fixed in position, you are emulating a solid. So if you look at the battle between kinetic energy and intermolecular forces, which one wins in a solid?
Intermolecular forces.
The intermolecular forces are winning. So in a solid, particles have very low kinetic energy and very strong intermolecular forces. That's what makes a solid a solid. Very strong intermolecular forces, very low kinetic energy. And if someone triple dog dares you, why does your tongue stick to the pole?
Because of the melting of peer pressure.
Peer pressure. The triple dog dare! The strongest of all dares. Some of you know what I'm talking about. The rest of you need to watch more movies.
Don't shoot your eye out.
They'll shoot your eye out. Yeah. Shoot your eye out, kid. Shove. So, and remember, we talked about this last time. Density of solids is about 1,000 times greater than density of gases. There's a lot of nuance in there. It's like, it's exactly solid? Exactly 1,000? No, not exactly 1,000, depending on what it is. But in general, density of a solid is about 1,000 times that of a gas, which is why you can put a tiny amount of dry ice in a 2-liter bottle and it'll expand to about 1,000 times the volume of that little chunk. Don't. Unless you're where it was. Okay, questions about solids before we move on to liquids. If you're happy with solids, give me a thumbs up. If you want to talk about it some more, wave your hand around. All right, liquids. So when you think about a liquid, you usually think that the kinetic energy is higher or lower than solids.
Higher.
Kinetic energy is a little bit higher, they're moving a little bit more, and the intermolecular forces are higher than or lower.
Lower.
A little bit lower. So they're still close together. They still have reasonably, relatively strong intermolecular forces, but not as strong as solids, and relatively low kinetic energy, but not as low as solids. Liquids are fluids. Fluids. Okay. When your mom says, get some more fluids, you need to stave off the coronavirus, drink lots of fluids. She's talking about liquids, right? But would it surprise you to know that gases are also fluids? A fluid is anything that can flow and take the shape of its container. So gases are also fluids. Does that make sense? So a liquid is a fluid, but a fluid is not necessarily a liquid, because a gas is a fluid too.
So is water wet?
Water is wet, and we'll talk about why right about here. Okay. But yes. Okay. Also, did you know that there are also solids that are fluids? Ketchup's a good example. Yes, so pitch is a good example. Glass is what we call an amorphous solid. It will actually form over time to its container. Toothpaste, gels are good examples. So yeah, Jello is a great example. So solids can also be fluids if they're allowed to flow. They are special kinds of solids called amorphous. Morph meaning design or form. A meaning not. So amorphous means no set form. Yeah, like the X-Men morph, he can become other things. Okay. Fluids or liquids have cohesion. So cohesion is a word we use when particles are attracted to the same particles. H2O attracted to H2O, that is cohesive forces. You remember cohesive forces when you do a belly flop? You're jumping off and you're like, I'm gonna do a cool belly flop. And right before you hit, you're like, oh no, water has cohesive forces. Meaning, water doesn't want to get out of the way. That's what I'm thinking when I do a belly flop. Like, oh shoot, I forgot. Yeah.
So like hypothetically, you get a belly flop into like Mercury, would that kind of get out of the way better and not sneeze as much?
Just the opposite, and we'll talk about that. Remind me, if I don't address that, remind me a little bit. We'll talk about that too.
Wait, I'm really confused about that whole thing. I don't know why.
Everything's a fluid. A fluid is simply defined as something that can flow and take the shape of its container. So glass, even though it's a solid, is actually the molecules are not fixed in place, they're constantly moving. And old windows is actually kind of a cool deal. Yeah, exactly, they're thicker at the bottom. You don't see this much in Boulder City. Well, maybe in some of the older towns, but your garage windows, if you tap them on top and tap them down below, the bottom one will sound thicker. They're like tap tap, dum dum, tap tap, dum dum. And sometimes garages, like wooden garages, will actually crack because the bottom will get thicker. Yeah. So. Yeah. Okay. So cohesion is attraction for similar molecules. Like water doesn't want to get out of the way. Fun fact: without water's cohesive forces, you could not swim. Because when you take your hands and you push them, the water molecules would get out of the way. The reason you can swim is because you're pushing the water, basically the water away, and the water's like, I don't want to go away. I don't want to move. So you basically get that resistance. Without that cohesive resistance, you can't swim. You're just like flailing through. Now, the reason you are wet is referred to as adhesion. Fluids also have adhesion, where particles are attracted to other particles. So cohesion is the reason why belly flops hurt. Adhesion is the reason why you're wet after getting out of the pool. Word?
Yeah, we say this all the time.
It's because he's channeling the 1990s. Like, word! Yeah. Word to your mama!
Yes, I got it.
Word up, word down.
People used to say right on. That always said right on.
Right on?
Right on.
That's more of a 70s thing. But I guess it popped up in the 80s and 90s. Right on, brother!
I don't know why.
What about totally radical?
That's an 80s thing. Yeah, that was an 80s thing. So, I guess some of your parents might be old enough.
My dad was born in 84.
Okay, so
65, yes.
all right, guys, let's talk about Mercury. So Brett brought up Mercury. I'll wait for you. Thank you. So Brett brought up Mercury. I really wish I could give you liquid mercury, but I haven't seen liquid mercury in person for about 15 years. Liquid mercury is nasty because it enters the gas phase. The gases get into your nose, get into your brain, and stay there forever. But mercury is really cool because mercury has extremely high cohesive forces and extremely low adhesive forces. If you had a pool of mercury, you could bounce a basketball off of it, and it would barely splash because the mercury molecules really want to stick together. And you could just walk on it. You'd be like, I'm walking on mercury. It would come up to your feet, but not much more. Okay? You realize that if there was a pool of mercury with a density of 19, you could walk on it and just go over your ankles, and that's it. I want to mention this because this was a big deal in second period. They seriously lost their minds about this. How much is it? Infinite. I've never seen it for sale. I mean, sure, you can buy it somewhere, but I've never seen it for sale. Dude, Amazon's not going to sell it to you. In fact, if you search for where can I buy mercury, there's a good chance you're going to be on a list somewhere. Because the mercury basically it vaporizes and it goes into your bloodstream, into your brain, and stays in your brain until you die. So, yeah. So here's the cool thing about walking on things that are more dense than you. Mercury has a density of about 19. You have a density of 1. Water has a density of 1. The reason that you sink into water is because you have about the same density. If you're really muscular, you might have a density of about 1.05. And if you're a big fatty, you might have a density of like 0.95. You might float a little bit. But for the most part, you're about the same density as water. Mercury is 19. So if you try to walk on Mercury, only 1/19 of you will be underwater, or under Mercury. Okay? Here's the thing about quicksand. The second period lost their mind about quicksand. Quicksand doesn't exist. Okay? It doesn't exist. The thing where you could you're gonna die in quicksand. The problem with quicksand is made of water and sand. Sand is very small rocks. So the density of quicksand is very high. So if you were walking along and you're like bloop into quicksand, you're like, well, that's inconvenient. It's gonna come up to your knees or your thighs, and that's no more. Because if quicksand has a density of at least, at the low end, 2, and you have a density of 1, that means only 1/2 of you will be under quicksand. You can't sink in quicksand.
I think we should.
Mythbusters already did. Yeah.
What about the Indiana Jones and the King of the Crystal Skulls?
I've been lied
Much Indiana Jones is interactive.
to. I've been lied to.
Yeah.
There weren't 3
Always
rocks.
use like
Aliens.
non-space.
Yeah. So yeah, quicksand is just one of those Hollywood things that they started. Yeah.
So what about the stories of people that have died in quicksand?
They're
They're
lying.
just stories. I don't know. Maybe they died because the pressure from all that stone on their legs caused them to like get some sort of crazy blood problem.
Or maybe they like freaked out so much they
Or maybe like get face down in the quicksand. Okay, phase changes. Guys, I need you to copy down this diagram. For those words, this is gas, solid, and liquid. This is evaporation, condensation, freezing, melting, sublimation, deposition. So copy this diagram. We're going to annotate it here in a second. Yes?
If you're pregnant, do you have a higher density?
That's a good question.
You know what?
Isn't it like something else in you that's just around the same density?
I don't know. I bet that's a quick Google search. But here's the thing about the density of a human being. Your bones are fairly dense because they're made out of metal. Your blood is fairly dense because it's got a little bit of metal in it. But most of you, like if you took all the air out of you, you'd have a density of about 1.1. But you have this giant chasm of air in the middle of you that reduces your density. So I figure, between the amniotic fluid, which is pretty rich in iron, and the blood that goes through, you actually might have a density that is a little bit higher because you'd have less air, but you'd have a lot more fluid that's rich in blood. So that'd be my guess, slightly higher.
She looked it up.
You looked it up?
Yeah.
Was it a quick Google search? Does the density go up or down? Did you look it up?
Oh yeah, your
Okay.
density goes up slightly.
Yeah. Because of all that iron-rich blood in your tum-tum. Okay, so what we're going to do is we're going to look at these diagrams and these changes, and we're going to compare their kinetic energy to their intermolecular force. So I'm going to write kinetic energy, and I'm going to write intermolecular force, and I'm going to write kinetic energy and intermolecular force, and I'm going to write kinetic energy and intermolecular force, and I'm going to do what the other ones do.